Hello everyone and welcome to the presentation of our work Walk2Map, extracting floor plans from indoor walk trajectories, which is a collaboration between the University of Zurich, the ETH Zurich, the University College London and Adobe Research. My name is Claudio Mura and I'm delivering this presentation also on behalf of my co-authors Renato Pajarola, Konrad Schindler and Niloy Mitra. In recent years, there has been an incredible proliferation of new products for the exploration and management of interior spaces, which have drastically improved a number of workflows related to indoor spaces, including virtual property showcasing, route planning, emergency management, and space planning. Obviously, the effective adoption of such workflows requires that suitable models of indoor environments be available. Such models must include information on both the architectural and the non-permanent elements. In fact, for many emerging use cases, we need so-called as-is representations, which describe the interiors according to their existing condition, and therefore must be constructed based on measured evidence of the underlying environments. The problem of creating as-is indoor models from measured data has attracted a lot of interest in the last decades, and has been extensively reviewed in a star at last year's Eurographics. The many existing techniques can be classified into two groups based on the type of input data they consume. One first group of approaches use three-dimensional or geometric inputs, like 3D point clouds. The models generated from this data can be very accurate. The main downside is that such inputs must be acquired using expensive devices such as 3D laser scanners in long and labor-intensive workflows, which clearly limits the pace at which one can create digital twins of existing interiors. A second group of techniques relies on simpler 2D visual inputs, like collections of panoramic images. These methods solve a more ill-posed problem, but they're quickly catching up with the methods based on 3D inputs in terms of accuracy. Images are clearly cheaper and simpler to capture than 3D scanned point clouds, but still a non-trivial data capture effort can be needed to adequately cover a cluttered environment. Overall, both types of approaches rely on complex data capture pipelines, which represents a bottleneck for a streamlined creation of as-is indoor models. What if instead of such rich 3D and 2D inputs, we could use something drastically simpler, some data that is in a way one-dimensional in nature and therefore much easier to capture, such as the walk trajectory of a person walking through an indoor space. A trajectory can be seen as a 1D object embedded in 2D space, if we consider the movement to happen relative to the 2D plane of the floor. A walk trajectory is simple, so it should be very easy to capture, and it does contain some evidence of the surrounding space. However, there are actually two problems with its use. First, a walk trajectory only contains sparse evidence of some walkable locations, and it's not at all obvious how to build a full-fledged indoor model from it. And second, it turns out that recording a walk trajectory in a GPS-denied indoor space is not at all a trivial task. The popular visual odometry techniques, either based on pure visual data or also using the readings of inertial measurement units, or IMUs, are of little help for our goal of drastically simplifying the data capture process, since the complexity of the data acquisition they involve is comparable to performing a video capture of the target space. In theory, one could use double integration to recover positional information from the accelerometer readings of an IMU. The problem is that this technique is not very tolerant to noise and requires the use of very high-end sensors, which are extremely expensive. Fortunately, there is a very promising line of research on data-driven inertial odometry that uses machine learning to correct the positional drifts that result from applying double integration to noisy accelerometer readings, such as the ones produced by consumer-level smartphones. This gives us a way to acquire indoor trajectories by simply walking through an indoor environment with a smartphone and processing the resulting accelerometer readings with a trained neural network. Every person can basically act as a citizen sensor capable of collecting the necessary data to extract indoor models. However, we're still left with the first question: how can we generate a floor plan simply from a walk trajectory? To tackle this extremely ill-posed problem, we present Walk2Map, the first approach to turn an indoor walk trajectory into a floor plan model that describes an indoor environment in terms of the 2D footprint of its interior space, the location of portals in its wall boundary, and the locations of furniture in its interior space. Our intuition is that interior environments are designed and furnished based on the way people live, work, and therefore also move inside them. We argued that it should be possible to use machine learning to extract from a walk trajectory the latent relation between the movement of a person through an environment and the location of the elements that make up its floor plan. The core of Walk2Map is a set of 3 neural networks that extract respectively the footprint of the interior space, the location of doors on the walls, and the location of furniture on the footprint. Each network is specialized on extracting a specific type of information, which makes it possible to tailor its architecture to the specific problem considered. The 3 networks are arranged as a cascade. Given an input walk trajectory, we project it onto the 2D plane of the floor and run it through the networks, augmenting it with the information extracted by the networks already applied. The first and the last steps, respectively interior space extraction and furniture extraction, recover information that relates to 2D regions of the floor plan domain, respectively whether such regions lie inside the boundary walls and whether they are occupied by furniture or empty. Whereas the second step, doors detection, extracts information defined on the wall boundary, which can be naturally represented as a curve. In other words, the first and the last networks are area-oriented, while the second is boundary-oriented. This suggests that different representations and different network architectures should be used for the 2 problems. We therefore adopt solutions similar to the one recently proposed in the work Planet by Wong et al. Given a room model, we embed it in a regular grid defined on its ground plane. Each cell is an area unit that can be occupied by furniture, free space inside the wall boundaries, or outer space. And each edge corresponds to the interface between 2 area units. Walls and doors should lie on such interfaces as they separate inner and outer space. We extract 2 different views of the room from this grid. An area-oriented view, where the cells are explicitly represented and that can be naturally encoded in a 2D image, and a boundary-oriented view, a graph in which each grid edge lying on the walls is represented by a graph node. The arcs of the graph connect nodes corresponding to grid edges that are either adjacent or opposite to one another on the wall boundary. We use the area-oriented image-based representation for the first and the last network, and the boundary-oriented graph-based representation for the second network. Since we aim to extract different information at each step, the features encoded in the input and output data items of the networks are different. The input to the interior space extraction network is essentially a one-channel image, which stores at each pixel the normalized inverse distance to the projection of the input trajectory on the 2D domain of the ground plane. The output is a one-channel binary image that encodes at each pixel whether the corresponding cell is inner or outer space, that is, whether it is part of the interior footprint or not. The input to the second network, remember a graph with a node for each discrete edge on the boundary loop, contains as per node features: the distance to the closest corner on the loop, the orientation of the edge, that is, a flag denoting whether it's vertical or horizontal, the 2D coordinates of the edge within the original discretized 2D grid, and the inverse distance to the walk trajectory for the adjacent block of 10 grid cells in the interior footprint. So for the node pointed to by the red arrow here, this would be the block of 10 cells here. We also set 2 features on each arc of the graph based on the properties of the edges corresponding to the arc endpoints. These are a measure of dissimilarity between the edge orientations and the distance between the edge positions on the 2D grid. The output of the network is also a graph with the very same structure, but with only one feature per node. That is, a binary label denoting whether the corresponding edge on the grid belongs to a wall or to a door. The furniture extraction network is also area-oriented and therefore also uses image-based representations as input and output. Differently from the first network, the input is a 4-channel image. The first and second channels contain the inverse distance to the walk trajectory and a binary mask encoding the inner and outer space. The third and fourth channels contain a labeling of the horizontal and vertical edges of the grid, where each label denotes whether an edge lies on a door, on a plain wall section, or does not correspond to a wall at all. The network output is a binary image that encodes whether the locations corresponding to the pixels are occupied by furniture or not. Note that the information provided as input to a network is built either from the input work trajectory or from the output of a previous network, allowing for a cascaded application of the networks at inference time. Having just described the representations used for the input and output of the networks, the natural question is, where do we get the actual data items for training and testing? One major problem in this sense is that there exists no dataset consisting of pairs of indoor walk trajectories and corresponding annotated floor plans. For this reason, we generate such a dataset from the Matterport 3D dataset, a collection of 3D scans of real-world indoor spaces that comes with room segmentation information as well as object-level semantic labels. For each valid room in this dataset, we compute a simulated walk trajectory on the ground plane, using an approach inspired by the recent work Discoman by Kirsanov and colleagues. We then convert the room into our grid-based representation, transferring the necessary labels from the initial 3D model to the cells and the edges of the grid. We also project the generated walk trajectory onto the grid and compute for each cell the inverse distance to the trajectory. Finally, from the set of all grid-based representations, we extract the training and testing sets for each of the 3 networks. Note that for the first network, we generate additional samples from the LeafFull dataset and use them in a curriculum learning strategy. We refer to the paper for the details. We also used an additional test dataset of 20 real-world trajectories, which we acquired using the Tango-based app developed by Jan and colleagues to create the ground truth data for their data-driven inertial odometry approach. We then performed a 3D scan of the environments in which the trajectories were captured and created the corresponding floor plans by manual annotation. We used the smaller dataset only for testing the networks trained with the synthetic data. Our networks are based on 2 architectures. The area-oriented network is a traditional U-net architecture that works on 2D images, and that is therefore amenable for the first and the last step, namely interiors footprint and furniture extraction. We use the classical 3-layer architecture with skip connections presented by Ronnerberger et al. For both networks. The only significant difference between the two is that we mask the raw output of the furniture network with the interior footprint before computing the loss, since the only meaningful predictions are those that refer to the interior space. The second architecture is more amenable for the detection of doors on the boundary wall loop. It is a graph convolutional network with 5 layers of dynamic edge-conditioned filters. This type of convolutional layers combines the features of adjacent nodes using weights that are dynamically generated by feature-generating networks. Their use, coupled with the addition of arcs between opposite edges in the boundary wall, significantly increases the accuracy of the network. We refer to the paper for further implementation details, including the size of the network layers, the details of the training process, and some basic post-processing techniques that we apply to the raw output of the networks. It's finally time to see some results. We will start with a qualitative analysis of the floor plans obtained from the Matterport 3D test set, that is, the test set belonging to the dataset of simulated trajectories on which the networks were trained. We consider here only a subset of the full test set. The top row shows the normalized inverse distance to the input trajectory, with y corresponding to a distance of 0. The second row shows the results produced by Walk2Map, while the bottom row shows the corresponding ground truth floor plans. Walk2Map is generally successful in recovering the correct room footprint and in localizing the main blocks of furniture. Small concavities in the footprint, as well as smaller furniture blocks, are sometimes missed or misplaced. Also, the borders of the furniture blocks appear generally jagged, But we want to stress here that we are solving an extremely ill-posed problem with limited training data and relatively simple neural networks. The performance of the door detection is best evaluated using this 3D visualization. There are indeed false positives, but they are always consistent with the other elements of the floor plan. For instance, it never occurs that furniture appears in front of a door, and this thanks to the structured cascade of networks used in our approach. The advantages of our structured pipeline become evident in the comparison against a baseline based on pix-to-pix, the well-known approach for general image-to-image translation. Here, we are basically solving the problem of converting the image of a walk trajectory into the image of the corresponding floor plan. As shown by these examples from the Matterport 3D dataset, this approach yields very noisy results with poor furniture localization, but most importantly, it happens systematically that walls do not form a closed loop or that doors appear outside of the wall boundary. This never occurs in Walk2Map, which always yields structurally correct floor plans. The natural question at this point is how the approach fares with real-world acquired data. Here we show some samples taken from our test set of measured trajectories, with the top row showing the 3D scans of the spaces in which such trajectories were recorded and that we used to create the ground truth floor plans. The main observations made for synthetic trajectories still hold. Furniture localization errors occur more frequently, but some of the errors here correspond to particularly ambiguous configurations, like furniture directly attached to the walls. In this specific case here, the network has reconstructed a group of desks arranged in a loop as a solid block. Clearly, it is virtually impossible to correctly reconstruct the empty space in the middle from just the input trajectory, especially if not enough similar cases are present in the training set. Overall, the reconstructed floor plans are structurally correct and all errors, such as spurious doors, are consistent with the reconstructed floor plan. Note that here we're processing measured data with networks trained only on synthetic data, and this domain shift inevitably leads to a certain drop in performance. The results seen so far are confirmed by our quantitative evaluation. We refer to the paper for an in-depth discussion, and here we will only stress that Walk2Map outperformed the image-to-image baseline on all steps, both on simulated and on measured trajectories. Our results look very encouraging, and it's exciting to see how much hidden information about an indoor space can be extracted from just a walk trajectory. Still, this is the first attempt at solving an extremely ill-posed problem, and there are of course a number of limitations. We work on a regular grid on the 2D ground plane, which means that we can model correctly only Manhattan world environments. Moreover, we only considered the case of single-room environments. However, the most pressing limitations are connected to the lack of suitable training data. We trained our networks using simulated trajectories, which obviously limits the performance on measured data. Besides being synthetic, the training data at our disposal were very limited in number, which restricted us in the choice of network architectures used. Walk2Map has just begun to scratch the surface of floor plan extraction from walk trajectories. It would be useful to extend the current pipeline so that it is capable of modeling multi-room environments, correctly detecting the footprint of each individual room and classifying it based on its type. Speaking of classification, another interesting extension would be to perform a fine-grained labeling of the detected furniture, and even the current portal's detection could be extended by including windows in addition to doors. Using richer trajectories that also include timestamp, height, and velocity would provide more input information to the networks and make these extensions more viable. In fact, most of these goals depend on the creation of a large enough training dataset of real-world trajectories paired with a corresponding ground truth floor plan. This is indeed a non-trivial endeavor, but it would greatly benefit the research in the field of indoor scene analysis and reconstruction, unlocking the true potential of Walk2Map and enabling the systematic and large-scale mapping of the world's indoor spaces. This concludes the presentation. Thank you for your attention, and I'm looking forward to answering your questions.